Good morning friends. Last class we discussed about the series resonant circuit, that is resonant frequency, bandwidth, quality factor and also different parameters variation with respect to the frequency. Now we go for the parallel resonant circuit. In this we have to calculate the resonant frequency. Two cases are there. One is practical inductor, fixed capacitor, practical inductor, practical capacitor. Practical inductor means a inductor in series with resistance. Similarly, practical capacitor means a capacitor in series with resistance. Now we go for case 1, practical inductor with fixed capacitor, that is nothing but tank circuit. So practical inductor with the fixed capacitor is also known as tank circuit. Let us consider a tank circuit, and so across the tank circuit a alternating voltage source is applied across it, that is V is equal to Vm sin omega t as shown in figure. So whenever we are applying a voltage V is equal to Vm sin omega t across tank circuit, an alternating current I is flowing through the tank circuit. This current distribution is explained with the help of phasor diagram. Let us take a vector V as the reference vector. Always the IC current through the capacitor always leading by 90 degrees, that's why 90 degrees IC, and remaining IL is exactly without a resistor is nothing but ideal inductor is nothing but exactly 90 degrees lagging, but it is not a ideal inductor, it is a practical inductor. That's why IL is a combination of IRL and IL. So that's why some angle phase pi, some angle pi. So the IL is nothing but vector combination of IL sin pi and IR cos pi. Now you have to calculate the resonant frequency. Go for the admittance of each branch. So now admittance of practical inductor branch YL is equal to 1 by ZL, that is equal to 1 by RL plus JXL. So 1 by RL plus JXL multiplied with RL minus JXL by RL minus JXL. So that is RL minus JXL by RL square plus XL square. So separate the real parts and imaginary parts and take another one, that is the admittance of another branch, that is fixed capacitor branch YC is equal to 1 by ZC, that is equal to minus 1 by JXC. So taken J as numerator, that is minus J, minus of minus plus, so J by XC is the admittance of this branch. Now total admittance of the tank circuit is nothing but YL plus YC, so that is equal to, so after combine these two and separate the imaginary part and real parts, so Y is equal to RL plus RL square plus XL square plus J into 1 by XC minus XL by RL square plus XL square. Simply say that at resonance condition is nothing but imaginary part equal to 0. So take imaginary part equal to 0 from that equation. So 1 by XC minus XL by RL square plus XL square equal to 0, but put XL is equal to omega naught L and XC is equal to 1 by omega naught C, like this, and rearranging these parameters we have to get omega naught square is equal to this one, and omega naught is equal to square root of 1 by LC minus RL square by L square. Put omega naught equal to 2 pi F naught. So F naught, resonant frequency of tank circuit, equal to 1 by 2 pi square root of 1 by LC minus RL square by L square. Suppose this circuit having practical inductor nothing but in series with resistance. There is no resistance in the sense, equation is F naught is equal to 1 by 2 pi root LC. So now the relation between the parallel resonant frequency with the quality factor is F naught is equal to FR square root of 1 minus Q square, 1 by Q square. So this is the resonant frequency for tank circuit. So this question is again asking another way. So derive the dynamic resistance of tank circuit. That is nothing but we have not calculated frequency, we just calculated impedance only. That is nothing but as usual manner. So a tank circuit is there. You have to calculate branch impedances, branch admittance separately, as we calculated before one. YL is equal to 1 by ZL, that is nothing but this one, and 1 YC equal to this one, and total admittance is YL plus YC, and this is the combination. Now at resonant condition imaginary part equal to 0. So imaginary part equal to 0, that is 1 by XC equal to XL by RL square plus XL square. So XL XC, so cross multiplying XL XC equal to RL square plus XL square, but XL equal to omega L and xc equal to 1 by omega c. Therefore RL square XL square equal to L by C, taking as equation 1. Now another part, that is real part. Real part is equal to y is equal to RL by RL square plus XL square. So now but RL square plus XL square is nothing but L by C from equation 1. Therefore y is equal to, so RL by L by C, that is C RL by L. This is the dynamic resistance or dynamic impedance of the tank circuit. This value is very high, so that's why dynamic resistance or dynamic impedance of the tank circuit is parallel resonant circuit is high, therefore current is minimum. So that's why this circuit is called as resector circuit, whereas in series resonance acceptor circuits. So but the parallel resonant circuit is also called as resector circuit. Now go for case 2, that is practical inductor and practical capacitor. A practical inductor is nothing but inductor in series with resistance RL, capacitor in series with resistance RC. Now a alternating voltage applied across it, alternating current is flowing through it. Now the current variations, that is nothing but admittance of each branch YL and YC, we also separately calculated. YL is equal to 1 by ZL, that is 1 by RL plus JXL. So rationalize that one, that is YL is equal to RL minus JXL by RL square plus XL square. So similar manner YC is equal to 1 by RC minus JXC. Rationalize that one, RC plus JXC by RC square plus XC square. Now total admittance is equal to YL plus YC, that is equal to, so and rearrange the separate the real parts and imaginary part. At resonance condition, imaginary part equal to 0. So that is XC by RC square plus XL square, XC square minus XL by RL square plus XL square. So there is nothing but put XL is equal to omega L and XC is equal to 1 by omega C, and calculating and rearranging all these things like this. So now getting lastly omega naught equal to 1 by root LC root of RL square minus L by C by RC square minus L by C radians per second. But we know that omega is equal to 2 pi f, so f naught is equal to 1 by 2 pi root LC square root of RL square minus L by C by RC square minus L by C heads. These two are the most important derivation in parallel resonant circuit. Tank circuit, that is nothing but practical inductor and fixed capacitor. So another one is practical inductor, practical capacitor, this one is. Now what is the property of resonant circuit is nothing but resonance occurs XL equal to XC in series resonance, but parallel resonance, so admittance, that's susceptance inductive susceptance equal to capacitive susceptance, and power factor is as usual unity, but current here is minimum, whereas in series resonance maximum, that is impedance is maximum, that is dynamic impedance. So under different resonant frequencies, that is tank circuit, practical inductor, practical capacitor, like this. So this is the two cases of resonant frequency in parallel circuit, most important questions. And next topic is variation of different parameters with frequency, exactly similar to that of series resonant frequency. In series resonant frequency, XL, XC, total net reactance, impedance, current, but here inductive susceptance, capacitive susceptance, net susceptance, impedance, all these things. So now go for the impedance Z value. So impedance Z is nothing but dynamic impedance of the parallel resonant circuit. Z is equal to L by RC. So it is decreases lower cutoff frequency, and it may be like this one. So at resonant frequency, this value is very maximum. Below resonant frequency, value is lower. Above resonant frequency, value is also lower. At resonant frequency, this is the maximum value. Another one is susceptance, G value. Conductance is independent of the frequency, similar to that of resistance. Resistance also independent of frequency. Here conductance is independent of frequency, that is straight line. G is equal to 1 by R. This is the straight line. So another factor is BC. So that is BL, inductive susceptance, is inversely proportional to frequency. So that's why, it represents a rectangular hyperbola. So this is XBL, BL in the sense XC. So similar manner BC is directly proportional to the frequency. So it is representing a straight line passing through the origin. So it is exactly, so in series resonance this is XL, so in series resonance this is XC, but in parallel resonance both are reverse, BL, BC and BZ, like this. So net susceptance at resonance, net susceptance is 0, similar to that of net reactance, BL minus BC equal to 0. Less than resonant frequency, circuit behaves as a inductive. Above resonant frequency, circuit behaves as a capacitive. Exactly opposite to that of series resonant circuit. And last, current one. Whereas in series resonant circuit, current is maximum at resonant frequency, but here current is minimum because of dynamic resistance. Dynamic resistance is maximum at at parallel resonant frequency. So another topic is, so quality factor, most important one, quality factor. Whereas in quality factor series resonance also calculated. Now quality factor of, so parallel circuit generally, so maximum energy produced inductor or capacitor by energy dissipated. These two elements are already in series resonance. I have to clearly tell about the quality factor. Quality factor is nothing but energy storage elements in inductor or capacitor. How much quality of energy is stored, and that stored energy must be dissipated in the resistor. That's why maximum energy stored in the inductor or capacitor divided by energy dissipated. Now coming for the inductor, as usual, go for the, so energy stored in inductor of Li square, but energy dissipated is IRM square RT, same details that one parallel resonant series resonant circuit. Now substitute all these things, but current through the resistor is IL is equal to V by XL, that is V by omega. This is the only change in quality factor. That's why quality factor is equal to R by omega L. So whereas in series resonant circuit, quality factor for inductor omega L by R, but here R by omega L, exactly reverse one. In similar manner for capacitance, what is the quality factor of CV square I square RT, but I is nothing but V by XC, that is the here change, that is 1 omega CR. Whereas in series resonant circuit, quality factor is equal to 1 by omega CR, but here quality factor is equal to omega CR, exact opposite. And quality factor for in terms of RLC circuit, so you know that quality factor is equal to resonant frequency by bandwidth, so 1 by 2 pi root LC by 1 by 2 pi RC, so R root C by L. Whereas in series resonant 1 by R root L by C, but here R root C by L. So this is the resonant frequency, quality factor for in terms of RLC. So another topic is bandwidth and cutoff frequencies. So the diagram, so inversely it is a V, that is nothing but below resonant frequency it is act as a inductive, above resonant frequency act as a capacitive, at resonant frequency act as a resistive. So but what is the impedance value at resonant frequency? That is Z is equal to root 2R in series resonance. Similar manner Y is equal to root 2G. So in series resonant circuit, Z is equal to root 2R, but Y is equal to root 2G. This is the in parallel resonant circuit. That is the identification value, Y is equal to root 2G. Now go for the derivation of bandwidth. It is a difference between F1 and F1 minus F2. That is BL minus BC is equal to G, but BL is equal to 1 by omega 1 L, BC is omega 1C. So like this, we are put the value. So this is equation 1. Like this, omega 1 minus omega 1 square LC by omega L equal to 1 by R. So cross multiplying that one and taking it is a quadratic equation. So therefore the roots of this equation, omega 1 square plus 1 by RC omega 1 minus 1 by LC equal to 0 is, so minus B plus R minus square root of B square minus 4AC by 2A. We are getting omega 1 is equal to minus 1 by 2 RC plus R minus square root of 1 by 2 RC square plus 1 by LC, equation 1. Similarly, so we are getting omega 2 minus 1 by RC. So omega 2 is equal to 1 by 2 RC plus R minus square root of 1 by 2 RC square plus 1 by LC. Now bandwidth is defined as the difference between these two cutoff frequencies. So equation 2 minus equation 1, omega 2 minus omega 1 is equal to 1 by 2 RC minus of minus plus 1 by 2 RC, that is omega 2 minus omega 1 is equal to 1 by RC. Put omega equal to 2 pi f F2 minus F1 is equal to 1 by 2 pi RC. The bandwidth of the parallel resonant circuit is 1 by 2 pi RC.